Okay, students, I know you had a lot of questions today about nuclear chemistry, all kinds of crazy stuff happening in the nucleus. And so there's a couple of things that I want to just review with you that people had questions about and that we had to go through a little bit quickly at the end of class. So the first thing is, how do I decide which type of radioactivity is most likely? And this is going to be, our choices here are alpha decay, beta decay, positron emission, or electron capture. And those are really the only three types that we're going to be concerned with. There are other types of radiation, but we're not going to talk about them in this class. And there's a pretty simple kind of flow chart here. First question you're going to ask yourself, question A. Is the atomic number 83 or higher? If so, what's going to happen? If it's 83 or higher, that means there are no stable isotopes. And the only way that we can make anything happen is by alpha decay. So alpha decay is going to be the predominant or most likely mode of radioactivity for elements that have an atomic number of 83 or higher. Second question we're going to ask ourselves, if that's not true, our atomic number is less than 83, we're going to look at the periodic table and we're going to find the average atomic mass from the periodic table. As an example, we can look at sulfur. For sulfur, it has an atomic number of 16. That's our protons. And our mass is going to be 32.065. So that's just from the periodic table. Now, I'm going to find that because this number right here, that's going to be close to whatever the mass is of the most stable isotopes. So if we don't know anything else, but we know that it's about 32, then we would assume sulfur 32 is a stable isotope. And other isotopes of sulfur, especially the farther away they get from 32, the more likely they are to be unstable. Why? Because the stable ones are more likely to occur in nature because they're more stable. So we expect the average atomic mass to be similar to whatever the mass of a stable isotope would be. Okay, so now let's say I tell you you have sulfur 37. Okay? And you want to know what's the most likely mode of decay. So now you're going to ask yourself, sulfur 37, this is heavier than 32. In other words, it has too many neutrons. And if it has too many neutrons, that means the most likely mode of decay is going to be beta decay because that turns a neutron into a proton. So that helps reduce the number of neutrons and increase the number of protons, getting us closer to a mass that we want to be at. Okay? Now, let's say instead I have sulfur 27. This one is lighter than 32, which means it has too few neutrons. Now, when I say it has too few neutrons, another way of saying that would be that it has too many protons, right? More protons than it's supposed to have for the number of neutrons that it has. And if it has too many protons, then we know positron emission or electron capture are the most likely, and that's going to be because they're going to turn the protons, a proton rather, into sorry, I'll delete that. Okay, proton into a neutron. And so by doing that, it's going to move the nucleus closer to the ratio that is stable. Okay, so that was the first piece that people were concerned about. 3 questions you're going to ask yourself. First question, is it an atomic number greater than 83? If so, we're going alpha. If it's under 83, we're going to ask ourselves, what's it supposed to be? I'm going to look on the periodic table and find out. And then I'm going to compare. Is it too heavy or is it too light? If it's too heavy, that means it has too many neutrons. It does beta decay. If it's too light, that means it has too few neutrons, too many protons, and so it will do positron emission or electron capture. Okay, now the other thing that people wanted to talk about that we didn't quite have, I guess there's 2 more things that we'll do. So one thing that I want to do is just show you a couple of practice problems. These are in the slides, but I skipped over them in class. They're like polls just to check that you can do the balancing of the nuclear equation. So I'm going to work them out for you so you can see how that works. So the one that we have here, we have uranium-235. We're going to bombard it with a neutron. And we're going to make strontium-90 and xenon-143 and something else. Oops. We don't know what the other something is, okay? So this is how I'm going to do this. We know the principle here is that our mass number, at least, the number of nucleons is going to be conserved, and our charge is going to be conserved. So what I'm going to do is set up an equal sign right here, and I'm going to add up this stuff on the top. 235 plus 1 equals 90 plus 143 plus x. We don't know what that is, but we can figure it out. We get 3 when we're done. X equals 3. Okay, so I know that my mass should be 3 of the thing that's over there. And now I'm going to do the same thing, and I'm going to do it on the bottom. I'll call this one y, but we're going to get 92 plus 0 equals 38 plus 54 plus y. And it turns out here y equals 0. So now I've got something 3, 0, and what the heck is that? Well, it turns out that's not really a thing. It's not a single particle, but it can be 3 neutrons. They have a charge of 0 and a mass of 1. So if you see something with a charge of 0, you should think neutron because that's like an uncharged particle. So our correct answer here for what we're going to put in our blank is going to be the 3 neutrons. And all I did was use the principles that the mass, the number of nucleons, the mass number is going to be conserved, and the charge is going to be conserved. So if I look at before and after, they're going to add up to the same thing. Okay, another example of this, we have words this time. Polonium 212, and when it's written this way with a dash, this is our mass number, is transmuted, which just means it changes which element it is, to lead 208 by what kind of emission? So we're going to have to interpret the words. We know that this thing is the first thing we're starting with, so that's going to be our reactant. And it's changing into this thing, so that's going to be a product. And they told us that this is emission, which means this is also a product. So we're going to have our polonium 212, and the atomic number is 84. And it's going to turn into lead 208. The atomic number is 82. And then we've got to find out what is this thing over here. So we do the same process. 212 equals 208 plus x, 84 equals 82 plus y. We get x equals 4, y equals 2, and we know what that is. It's an alpha particle. So alpha particle is the thing that we were missing from our equation. Okay, So those are examples of balancing the equations. Last thing that we're going to talk about is when you have a series, a radioactive series. And this is a thing that we were doing right at the end. We had this question and we said we're starting with uranium-238. The atomic number is 92. And it's going to turn into lead-206. The atomic number is 82. And it's going to have X alpha emissions and Y beta emissions. So we've got to solve for X and Y. How many alphas and how many betas? Now, if we just look at the symbols here, we can actually see our beta does not change the mass number. But our alpha changes the mass number. Both of them are going to change the charge. So if we started by dealing with charge, then we'd have a problem, right? Because they're both changing it and it'd be hard to figure out which one would do what. But if we start by thinking about the mass, then we can figure out how many alpha particles we have. Figure out then what that does to the charge, and then how do we need to adjust the charge to get to where we want to be. Okay, so I'm going to start by thinking about alpha particles. I know I'm going from 238 to 206 plus X times 4. X being the number of alpha particles and 4 being the mass of each alpha particle. So when I solve for X, I'm going to get 8 alpha particles. So I know that I can replace this with 8. When I replace that with 8, we'll do like a partial decay for what we're going to get, right? So we have our 238, 92 uranium, and we're going to get our 8 alpha particles. And I want to know what's the thing that we get also. So when I do this math, I end up getting osmium, which is number 76. It has the mass of 206, which is what we're going for, but it is not lead, and we're supposed to be able to get to lead. So now I know I'm having my osmium 206, 76, and I'm going to have lead 206 be the product, and I'm going to have Y numbers of beta particles. So 76 equals 82 plus Y times -1. And I end up with Y equals 6. So when I do my complete equation up here, I can replace Y with 6. 8 alpha particles and 6 beta particles in this decay. Same principles applied. It's a little tricky because we know multiple things are happening, so we always want to start with our alpha because that's going to tell us how the mass is changing, and then we can figure out the charge afterwards. So we get this kind of intermediate. This is like not really a product. Just the intermediate that we're talking about when we get through with our alphas before we take care of our betas. Okay, that is everything from our class today. We finished that up. Oh, I said I would also talk about the summary. So, why are some nuclei unstable? Let's do it. Okay, I can't write. Oh, okay. Why are some nuclei unstable? Well, it has to do with the ratio of protons to neutrons. And there's some, we call them kind of like magic numbers where you have the right ratio and those end up being stable. And those are represented by the stable isotopes that we see like on that graph that we saw today with all of the isotopes. They were the black ones that were stable. So it has to do with the ratio. And if they have a correct ratio that's stable, then they're stable. And if the ratio is off somehow, then they are not stable. So that leads us to our next question, which is, let's say we have a neutron-rich nucleus. What type of decay would we be likely to see? Well, if we have too many neutrons, then we want to be able to get rid of them or turn the neutrons into protons. So what will turn a neutron into a proton? That happens when you have a beta decay. So beta decay would be the most likely mode of decay for a neutron-rich element. How do you know it's neutron-rich? It's going to be heavy, heavier than what we see on the periodic table. What if we have a neutron-poor nucleus? What type of decay would we expect to see then? Well, if we don't have enough neutrons, that's like saying we have too many protons. So we want to turn a proton into a neutron, and that happens when we release a positron. So positron decay is going to be the most likely mode of emission. And we'll just put parenthetically here, or electron capture, which accomplishes the same overall change, turning a proton into a neutron, just by a different mechanism. And you guys don't have to distinguish between when it would be positron emission or electron capture. You just know that those both accomplish the same kind of thing. Now, what if we have a very large nucleus? What type of decay would we expect? Well, when we get into those very large nuclei, there aren't any stable isotopes, which means that we've got to get rid of mass and charge, both of them. And so that means we're going to end up with alpha decay being the most likely mode. Okay, that's everything for today. Thanks for listening. I hope that's helpful, and good luck with your exams.